Alright, we're in unit number 6, working through energy transfer diagrams, and I've got a lot of demonstrations. Some of these I can do on this video, some of these are just kind of classroom type diagrams, but I'll do the best job I can at doing as many as I can for you. So the first one is demonstration, and it's two metal spheres. And so what I've got, you can see them right here, are two metal spheres, basically solid. They're pretty heavy, and when we talk about energy transformations, we're talking about energy being transformed from one form to another. So from kinetic to gravitational, gravitational to chemical, chemical to thermal, something like that. That's what we talk about when we talk about energy transformations. And so what I'm going to demonstrate for you is, this is going to be kind of a tough one for me to demonstrate in a video, but we'll give it a whirl. I've got a piece of paper, and what I'm going to do is I'm going to take these two metal spheres, you can see them here, and I'm going to pound them together. And before I do that, I want you to look at this piece of paper. This piece of paper has no holes in it at all. And as soon as I pound these together, you're going to notice some holes. And so let me try to do it here. And there it is. And you'll notice that, boy, I wish I had smell-o-vision on this video, because you could actually smell that, and you can kind of see it here. Let me see if I can zoom in just a little bit, and then see if I can put this into focus. Yeah, you can see it here a little bit. You can see that the paper was burnt a little bit, and if you were here in person, you could actually smell the burning paper. And the question is, well, why did it burn? Obviously, I didn't have a match, and I didn't light it on fire. So how did that all happen? Well, when I took these two spheres and I pound them together, even when I'm doing it right now, I create some of that. I take some of that kinetic energy, energy of motion. I take some of that kinetic energy, and it is transformed into heating up anything that's between these two metal balls when they're sliced or pushed together. And if I put a piece of paper between them, that kinetic energy gets transformed into thermal energy, and as a matter of fact, that thermal energy is high enough to cause this paper to burn. Now, I've never done this in class, and the whole piece of paper catches on fire, but it's enough to create holes in the paper, and that's an energy transformation. Some other examples of energy transformation. So that first one was kinetic into thermal, and actually it's another one too. You can actually hear it. So it's kinetic into thermal and also into sound as well. Sound is a form of energy. Here's another one. It's a McDonald's toy that actually a former student brought in a while ago. And so what I'm going to do is I'm going to go ahead and spin this a little bit. And when I'm spinning this, there's a spring on the inside. You really can't see the spring, but I'm storing energy inside the spring. So I have spring potential energy. And when I let this go, it transforms that energy into sound and actually kinetic energy. So I'm going from rotational to spring, and then spring into kinetic and sound. So that's just an example of transformations. So let's go ahead and define those real quick on the page, and then we'll run through some diagrams. So energy transformation. This is when energy switches from one form, that's why we have the word form in there, one form to another. Energy transfer is when energy moves from one object to another. So energy goes from one thing to another thing, one object to another. Energy transformation is when it stays within an object, but you have a different type of form. So let's go through these and see how these kind of work out. So trace the energy transformations of a basketball when it's dropped. Alright, so when we did this in the previous video, if you drop an object and let it fall, it has gravitational potential energy at the top, so we're starting off with gravitational potential energy. As it falls, it's transformed into kinetic energy. When it hits the ground, some of that energy is transformed into thermal energy. Okay, it heats the room up, produces a little bit of sound. All right, and then it goes into some elastic potential energy. How about EPE? There we go. All right, so when it hits the ground, it's elastic, sound, and thermal. This elastic, any elastic that remains, then goes back into kinetic energy. It has movement, so it can then move up, and it goes back up to gravitational potential energy. So every time it goes, this is at the top, this is at the bottom, this is back at the top, not as high as what it started at because I transferred some of that energy into sound and thermal, so I can't go back up to as high as what I started at. But that's the energy transformation diagram. You're accounting for all the forms of energy that occurred. All right, the next one, energy transformation of a flashlight. So if you turn a flashlight on, where does all the energy come from and where does it go? Well, a flashlight is going to operate off of batteries, and batteries are a form of chemical energy. And when you turn it on, there's a little bit of electromagnetic energy. So it goes from chemical potential energy to electromagnetic energy, and then it produces light. And those that know this, and also some thermal energy. So chemical energy produces electromagnetic energy because there's wires in there, and then that electromagnetic energy turns into light and thermal energy. Trace the energy transformations of a hamburger. Well, hamburger, and I'm getting hungry right now, hamburger is chemical energy. You eat that hamburger, it goes inside your stomach digests it, and then it transforms it into energy you need to operate your body. So the fact that I'm moving my hand right now, that comes from the chemical energy of that hamburger. So that would be kinetic energy. The fact that I can speak is sound energy. The fact that my body is warm is thermal energy. You know, like when you hear someone dies, they've assumed room temperature. Well, their body's not producing any more energy because they're not eating anymore after they die, and so they can't maintain their body heat, and so their body's going to cool off to room temperature. Other sources of energy recruit life to live a more comfortable life. Other forms of energy is coal. When I lived in Springfield, Illinois, the power plant that provided the electricity for Springfield was a coal-powered power plant. And so it would burn coal. That coal then would produce heat. The heat would then boil water, and then that steam that's being produced from that boiling water would turn a generator and produce electromagnetic energy. And so, there was basically railroads that would be constantly bringing coal into Springfield all the time and giving us the energy to be able to operate Springfield. Here, close to us in Byron, Illinois, is nuclear. And that's a little bit different. We'll talk more about it later on in this chapter, but we can destroy mass. So we destroy a little bit of uranium, and we produce energy, and that energy is then transformed through a generator to produce electricity that would power homes throughout the Byron area. Trace the energy transformations of a generator. Now, I've got a better generator that we actually use in class, but I'm going to go ahead and show this one so you can actually see. I can get this one in the video, or yeah, in the screen here, and you can kind of see it a little bit. I've got basically it almost looks like a pencil sharpener here, but it's got a little bit of a thing I can turn on the end here. And now this one doesn't work, but you get the idea. And then I've got a light bulb. And so if this were actually working, I could actually rotate this, and as I rotate this, I could actually turn this light bulb on. And so I would be transforming, let's see, kinetic energy, or rotational kinetic energy, into electromagnetic energy. Where did I get this energy from to turn it? Well, it came from the breakfast I ate this morning. So I would turn this, and that would produce electromagnetic energy over here. So let's go ahead and write that down. So trace the transformations of energy. So we're going to start with rotational kinetic energy, and go into electromagnetic energy, and then into light, and then you know that light produces a little bit of thermal as well. All right, the next one, trace the energy transformations through a PV cell and fan. And I have one over here. This one, since I'm not by a window, it's not going to work real well, but I have some thermal or some PV cells, photovoltaic cells, kind of like the cells that would be on top of a roof that would be collecting energy from the sun. And then all of that is connected into a fan. And so if this were by the window, I could collect energy here, solar energy. It transforms it into electromagnetic energy, that's the wires, and then I would be able to make this move. That would be rotational kinetic energy. Let's go ahead and jot that one down. So trace the energy transformation through a PV cell fan. So I would have solar. So solar would be electromagnetic energy, and then it would be to another form of electromagnetic energy, which would be electricity, and then into rotational kinetic energy. Next page. Compare the energy transfer diagram of a CFL light bulb to an incandescent light bulb. All right, so let's analyze those real quick. Incandescent light bulbs. Those are the light bulbs that it's a light bulb you saw earlier, which is this guy. Unscrewing it. So this is an incandescent light bulb. These are the old light bulbs. And then a CFL light bulb is a light bulb that it's got the curl to it. And that's the one that the government is pushing us to use. So what's the advantage of a CFL over a light bulb? Why is it that the government is encouraging us to use CFLs as opposed to incandescent light bulbs? Well, let's take a look at what an incandescent light bulb does and put some numbers on it. So an incandescent light bulb is going to start off with electromagnetic energy because you plug it into some sort of power source. And then let's say it has 60 watts of power, so it's using up 60 joules of energy every second. Well, when you turn it on, some of that energy goes into light, okay, which is electromagnetic energy, and that's good. That's a good thing. We want that. But what we don't want is thermal energy. So some of that energy that you get from electromagnetic energy is transferred into thermal energy. We don't want to turn a light bulb on to heat the room up. We want to turn a light bulb on to produce light. And so we want this to be at maximum, and we want this to be at minimum. Well, in an incandescent light bulb, what happens is if you have 60 watts of energy coming in, or 60 watts of power coming in, basically 6 of those 60 become light. Well, that's only 10% becoming light. It's only 10% efficient, and that's not a very good thing. We want that to be maxed out. We want that to be as large as possible. Down here, thermal energy, we want this to be as small as possible. Well, if we start off with 60 and we finish with 6 over here, well, then this is going to be 54 watts of thermal energy, and I don't want that. That's a lot. That's going to be 90% of my energy that I start with is going to be transformed into thermal energy. And that's very inefficient. Well, that's what CFLs do for us. A CFL, let's say we have a typical CFL of maybe 60 watt CFL, and that'll be, we're going to start with the electromagnetic energy, just like we did for this one over here. Now notice, this is 60 watt light bulb. A 14 watt CFL doesn't need as much energy, and I'm going to show you why. Because when you turn it on, some of it becomes light, which is electromagnetic, and some of it becomes thermal energy. But the amount that turns into light is going to be a greater portion of this 14 than what it was for the electromagnetic. And in this case, 6 of those watts from the 14 becomes light. Well, that's if you do the math on that, that's 43% of the energy going into light. Notice, still produces the same amount of light, but we don't have to draw as much energy at the beginning, which is a big advantage of a CFL. And then let's see if I can do the math here. Well, that means that that 8 watts still undesirable. We don't want that. but it's definitely not. Let's see, that transforms into 90%. No, I said that wrong. Try that over. 50. So 57% of this energy gets transformed into thermal, while 90% over here on the old traditional incandescent light bulbs transform into thermal. Well, we want this because more of the light, 40%, 43% of it goes into light as opposed to thermal energy, and that's a good thing. Okay, down here you're going to need an equation for this worksheet that you're going to do in class or for homework, and that's going to be energy equals power times time. And then you're also going to know that an additional unit of energy is going to be a kilowatt hour. Let's see if I can write hour like it's supposed to be written. So add this to your equation sheet, and then kilowatt hour as well as a unit. And there it is. We'll start with talking about conservation of mechanical energy in the next video.